Okay, this lecture just took 26 minutes. I'm going to try to cut it down, but so I'm going to talk fast. Um, but it's full of some fun stuff, and I just can't pass up the fun. But mainly, I hope that most of this material in Chapter 21 is review for you people. I'm going to throw in a lot of extra stuff that'll look scary, but but I'm just telling you about coming events, so you don't need to get all tied up in the scariness. But it used to be that chapters would start with an introductory essay. They don't do that anymore, but I thought this one was fascinating. It has to do with the fact that if you crunch wintergreen lifesavers, they give off sparks. And then they went through with the physics of that. And the physics is like this. When you take a sugar crystal and fracture it, it tends to be that the two parts of the sugar crystal don't come off neutral, that one ends up with too few electrons and the other with too many. And that potential difference then causes a spark to jump between the two halves of the sugar crystal. And that spark then excites nitrogen atoms to jump to a higher energy level, and then they jump back down and they give off ultraviolet radiation. That's called scattering. But of course we can't see. This happens every time a sugar crystal gets crunched, but we can't see ultraviolet. However, in the presence of wintergreen oil, that ultraviolet radiation will then excite the atoms that make up the wintergreen to jump to a higher energy level, and they jump down in two steps, which you may or may not recall is called fluorescing, and one of those steps gives off visible light. So I think that's a wonderful, wonderful detail about what goes on. So we're talking about electrons. And in the second half of the this semester, we're going to get into magnetism. And I thought it's just cute to me to know where this comes from. Electron is the Greek word for, do you remember from last year? Amber, the hardened pitch of pine trees, also called rosin sometimes. And this is a material which, if you rub it, it becomes very, very electrified. And so they named this steady for that material, which works very well. And magnet comes from a region of Greece called Magnesia, and they found lodestones there, that is magnetized rocks, and so they named the study of magnetism after the place where they found the first magnets. That's also where magnesium gets its name. They found a salt of magnesium for the first time in Magnesia. So charges, charge, electricity comes in positive and negative, and you recall that it was Benjamin Franklin who gave it that name, and it was also Benjamin Franklin who decided that it was the positive fluid that was the one that moved, and thus we have this problem that when we draw arrows like the direction of a current, that is exactly the opposite to the direction that the negative electrons are moving. But it wasn't until 150 years after Franklin had made his nomenclature choice that we discovered that electrons are on the outside and protons are on the inside of an atom. Hans Christian Ørsted is the one who discovered the relationship between electric current and magnetic field. And then this guy Ampere was very intrigued by what Ørsted had done, and he puts some mathematics onto that relationship. Michael Faraday discovers the Scotsman. Oh, so is he. Well, maybe he's an Englishman. I don't know. Michael Faraday. I think he's a Scotsman as well. discovered many relationships between current and magnetism, but without any mathematics to what he did, and Maxwell comes along and puts the mathematics on. As you will see on the next page, what are spoken of as Maxwell's equations have other people's names on them, but he made it a mathematical unity, and he is much lauded for it. Then comes Heinrich Hertz, who said, hey, we can take this electromagnetic radiation and we can actually make it radiate. And so he is the first person to make a spark in one place, cause it to transmit through the air and get a spark at the other place. So the transmission of electromagnetic waves. And then Marconi and Tesla, Nikola Tesla, I don't know Marconi's first name, they took this notion of electromagnetic waves and made it a practical application, what we call radio. Usually Marconi gets credit. Tesla thinks he should get credit. So the capstone, the culminating event for this semester, this study of electromagnetism, will be that you will have command. It's okay if these look scary to you now. By the end of this semester, you will feel comfortable with them, you will understand them, you will be able to explain them to the other people at the dinner table. It's going to be meaningful. And look at that weird integral that you've got there. Oh, I can't wait. What an exciting semester. Usually, and you see other people's names, that these are what are called Maxwell's equations. Usually they're written in a derivative form instead of an integral form. And if you take multivariate, then you will get to these, and these are called divergence. This differential operator dotted with the magnetic field or electric field. And these ones are called curl. And I am so pleased. It was just in 2019 that I hitched up my loins and went to battle with this and came out feeling like I understood what was going on here. So at the very end, just for the joy of it, we will look at these, but you will not be responsible for the differential form. This does seem to be the more popular form of it. So whenever the book has something very profound to state, they put it in a box like this with a green hand pointing at it. And here's the profundity of chapter 21. Like charges repel and opposite charges attract. Whoa, that is so sweet. Unfortunately, it's a misrepresentation of what is going to be profound. Will get confusing soon enough. But would you please apply that to do this checkpoint? Coulomb's law, which I hope you recall from last year, has to do with the force between charges. We're actually going to do it for electric field, but I hope this looks familiar to you. It was the force between two charges. It looks very similar to Newton's law of universal gravitation, which was the force between two masses. But actually, this year, Coulomb's law is going to look like this, where Coulomb's constant gets replaced by this thing. And sometimes we will write this. You may like to go back to write this, but I would encourage you to learn this new form of Coulomb's law. Don't forget that this r is the distance between those two charges, and by the location of those two charges we mean the centers of those two charges, so r will again be the distance between their centers. Notice the magnitudes that, just as last year I encouraged you not to put signs in when you were calculating the magnitude of the force, so too the book. That you can get whether that force is attractive or repulsive by applying the fact that like charges repel and opposite charges attract. This curious thing here has a name. It is called the permittivity constant. Sometimes it's written to look like that. It is not necessary that you put the naught on it epsilon naught, because we will never deal with any other epsilons besides the permittivity of free space. However, when we get to magnetism, we're going to have a very similar formula, which is going to have the permeability constant, and you will need to put the naught on it because we will also deal with a mu, which is not the permeability of free space. It's called the magnetic dipole moment, and so you will need to be careful about that. You don't need to do anything with that right now. Shell theorems. Now here's the green hand again. Yes, these are important, and these are a little bit harder. You, I hope, recall them from last year, but if not, you memorize them in a hurry now. It says if you've got a shell that is uniformly charged, it doesn't have to be circular, but if it's a conductor, it would need to be yeah, I think it does sort of need to be. At any rate, the charge has to be on it uniformly. It doesn't have to be a conductor or an insulator. Both will work. But if you are outside of that spherical charge, that shell, then the forces you feel, the fields that are created, are as if all of the shell's charge were located at its center. In the same way that when we deal with gravity, we act as if all the Earth's mass is at the center of the Earth. In fact, these theorems were created by Gauss for dealing with gravity and not electricity, but they apply. If you have a uniform shell of charge, could be hollow, could be solid, doesn't matter. If there is uniform charge on that shell, well, if it's not hollow, it's not a shell, sorry, then, and you are inside of the shell, then you feel no force at all. And there is no field from those charges uniformly distributed over the shell. Okay. On the outside of a uniform shell, as if all the charge were at the center, at the inside of a uniform shell, no field, no force. You must memorize these. You must be able to apply them, and you must be able to state them accurately. Not your life will end. You'll just lose points. Recall that you will hopefully recall from last year that charge is quanticized, that it comes in multiples of the charge on an electron, and you cannot have any charge other than the charge on an electron. Very quickly, Robert Millikan, doing his oil drop experiment at the University of Chicago in 1908, worked this out. I also expect you to recall the definition of a field. If you don't recall it, you must memorize it in a hurry. That a value assigned to every location, that's what makes it be a field. You must find some way to make this meaningful for you. That in the case of a point charge, now capital E is the symbol for electrostatic field strength. That field strength, that value that you assigned at every location, if it's from a point charge, is going to be the charge times Coulomb's constant divided by the distance that you are away from it squared. Or here you are with this year's statement of Coulomb's law. But notice, it's Coulomb's law with the second charge missing. The second charge has been divided out. Okay, those are sweet formulas, but they only work for a point charge. In general, the definition of field strength, electric field strength, will be stick a second charge in there. We call this a test charge. See what force it experiences, and then divide the charge back out, which might seem identical to what was done here, but it's not. You must embrace that this is the definition of field strength. Here are pictures of electric fields. Notice the arrows. That's the direction a positive would go, due to the nomenclature of Ben Franklin. That the field strength would be tangent to those field lines. And you say, wait a minute, Mr. Houghton, a field is supposed to have a value assigned. Well, it's hidden in here. It's in the density. Where the lines are close together, that's a high density, that's a strong field, big number. Where they're further apart, that's a lower density, small number for the field strength. Here, in between two positive charges, there's going to be a place where the field is 0. So we're going for very low density there of the lines. I would also expect you to look at these and know that this, if I had not put the two positives, I would expect you to recognize by looking at the diamond of rejection that this was like charges, and this one from the pumpkin of embrace was unlike charges. I expect you to be able to draw these fields. I expect you to, given the fields, to know what it says about those charges. Notice again, the field strength is tangent to the field lines. The magnitude, the value from the density of the field lines. And in this chapter we also introduce a field that a charge would experience very close to a plane, a uniformly charged plane of charge. If you get up close, this plane looks to be infinite. And it turns out that for an infinite, uniformly charged, infinite sheet of charge, you get a field that looks like this. What about the density? It's everywhere the same density. That means everywhere the same field strength. Notice all the arrows are pointing in the same direction. This is what we call a uniform field. And that is the kind of field, I expect you to know this, a infinite sheet of charge will get you a uniform field where it doesn't matter how close or far away you are, you get the same field strength. But this would be the kind of field that you could not determine its strength any other way than by putting a test charge in, seeing what force it experiences, and then dividing the test charge back out. Okay, I've probably spent too long, but this is just too cute. When you have this word, triboelectricity, it means electricity from friction, from rubbing. Like you take a cloth and rub it on a piece of plastic and it becomes electrified. That's triboelectricity. Well, this bee has been triboelectrified, probably just by flying through the air. He rubbed against air molecules and he became charged. And that bee comes into a flower and pollen grains jump off of the anthers onto the bee. Because there is a field around that charged bee, and that field induces local charge. You remember this from last year? Induces local charge on that pollen grain, and because the opposite charge is closer, that force is greater than the repulsion to this. Remember, it varies inversely as the square of the distance. And so the pollen is attracted to the bee and it sticks all over the bee. But then the bee comes back to another flower, and in the flower, the female structure, the stigma, is grounded. But the anther, the male part of the flower, is not grounded. And so you get this inducing charge there. But when the bee comes back into the flower, the field from the bee induces charge in the stigma, something that did not happen in the anther because it's grounded and it pulls all this charge. In fact, so much charge that the field that is induced, that the field that is created from the charge being induced in the stigma, pulls pollen grains off of the bee and onto the stigma. And in this way we avoid having the flower colonize itself, which is bad for genetic diversity. And so I thought that was fascinating. Thank you for your time.